Hi pre-calculus honors. So today we're going to talk about section 1.5, parametric relations and inverses. Go ahead and read the objectives. We're going to be able to find functions parametrically and find inverses of functions and relations. So we're going to start with parametric relations defined parametrically. Now this is just an introduction. Later on in a future chapter we're going to devote much more time to parametrics. So this is an introduction. So some of you might look at this and think, I'm not really sure what's going on. So these are parametric equations. So we have x and y both defined in terms of t, and we have an interval for t. So again, this looks strange to us. So what we're going to do first is try and fill in this table. I picked some values for t in this interval and decide what would x and y be. So I'll get you started. For example, if t is -2 and x is 3 times t, x would be -6 when t is -2. And if y is t squared plus 5 when t is -2, that would be y is 9 when t is -2. So go ahead and pause the video and fill in the rest of the table. Okay, welcome back everyone. Hopefully we have the table all filled out and maybe this mystery is getting a little bit more clear. So what we're going to do next is we're going to find an algebraic relationship between x and y by eliminating the parameter. So in other words, I would like y in terms of x. So we're going to eliminate the parameter t. Okay, so I would take a look which equation looks easier to isolate the x or to isolate the t. I believe the first one would be easier. So we're going to let t equal x over 3. Okay, so now if I take my second of my parametric equations, everywhere I see a t, I'm going to substitute x over 3. So we just eliminated the parameter and we have y in terms of x. So what I would like you to do next is try and graph. You could use the table, what your knowledge of parent functions and transformations, and then go ahead and grab your calculator and support this. Actually, you might need help with the calculator, but I need to show you how to use parametric mode. So let's try without a calculator first. Go ahead and pause the video. Okay, so hopefully you realize that your graph looks something like this when you plotted those points. Notice you don't want to put arrows. This is very important because your t interval was from -2 to 2. So we have endpoints at 6, 9 and -6, 9. Okay, so let's go ahead and grab our graphing calculator. So I actually put this in for you. Go ahead and choose mode. And when you go to the mode, notice that you could cursor down to parametric and you want to highlight parametric. So we're not graphing functions right now necessarily. We are in parametric mode. So go ahead and highlight this. Now when you go to y equals, notice it looks very different. So I went ahead and typed in 3t and t squared plus 5. Okay, so after you do that, again, notice that the t is on the x, t, theta, n button right here. Okay, so if you type in 3t and t squared plus 5, now when you go to window, you might want to do a zoom 6 or something to get started. I typed in that t interval of -2 to 2. Now t-step, we're not really sure what that means right now, so let's just put 0.1 and we'll explore that later on. And again, x-min to x-max, I just went -10 to 10. Let's take a look at what the graph looks like. There you go. Okay, so I thought I would maybe explore with trace a little bit to help, but with this function it might not be quite so obvious. So I'm actually going to unhighlight this or just turn it off. Notice when you unhighlight it, if I just choose one of those two equations, they both turn on or off because again, they're parametrics that work together. You need x and y, both x and y in terms of t for a parametric equation. So here goes. Or I should say to find something parametrically, you need x and y in terms of t, both equations. So here we go, everyone. We're going to go ahead and graph this. T and t plus 1, it's a line, okay? And if you look at the trace, notice as you're tracing, you can take a look at those values, right? And as we're looking at different values for t, since I defined x and x equals t, right? We have different points. We have points for x and y, both in terms of t. So again, hopefully that helped a little bit. We are going to do another example now. So go ahead and go to the next example. Okay, so we are going to explore with our calculator a little bit. So go ahead and type x equals cos t and y equals sine t. Make sure you go to your mode, and let's make sure we're all in radian mode. Let's take a look at the window. I decided to go from 0 to 2 pi, and right now the t-step is 0.1, And again, we're going to talk about that in a little bit. I just want -5 to 5 for x's and y's. Let's just take a look and see what the graph looks like. Okay, so first of all, this looks like an ellipse, which we studied last unit. But if you remember from trigonometry, right, when we said, we had the x and the y coordinates for the cosine of theta and the sine of theta, etc., it was a unit circle. So what's happening here is you have a rectangular screen. So if you do a zoom square, that'll square up your screen a little bit and take into consideration that it's a rectangular screen, and there you go, it's a unit circle. Okay, so go back to the window now, and I want you to see what would happen if you didn't go from 0 to 2 pi. Let's say you went from 0 to pi. So before you try it, go ahead and have a hypothesis. What do you think would happen? So pause the video and give that a try. Okay, so let's say, for example, we had 0 to pi. When you take a look at the graph, there you go. So notice it's only going to graph those x values from 0 to pi. What if you, for example, went negative pi to negative, let's see, how about this? How would you make this particular graph maybe just graph the right side of that circle? Go ahead and pause the video and see if you can make it do that. So for example, if this is our goal, how would we do that? Let's give it a try. So I'm going to go to the window, and I think I'm going to try negative pi over 2. To pi over 2. Let's see what happens. There you go. Okay, so now we're going to talk about the t-step. So let's go back to window. We'll go back to 0 to 2 pi just so we get the whole unit circle in there. Okay, so what if I change this t-step? I'm not really sure what's going on with the t-step. Let's just try what would happen if I made it really small, like 0.001. If I go to graph right now, you might think my calculator's broken, but no, actually, do you see it? It is working. Oops, cancel. It is working, it's just moving very slowly. Okay, so your calculator, you're asking it to go from 0 to 2 pi, which is about approximately 6, and 6.28 approximately, and it's making quite a few calculations every 0.001. So let's give the calculator a break. We don't want to just sit here all day. So you can hit on to stop it. And if you go to window now, okay, poor calculator, you're working too hard. Let's go like maybe, I don't know, 1.5. Why work so hard? Now let's take a look at the graph. Oh my goodness. Okay, so do you see how it's not a circle at all? So it's not very accurate. That's not enough calculations. It just connected. It made four or five calculations and connected them all together. So what we're going to do is we're going to try and find a happy medium where you find a t-step that's not so slow that it takes forever, but not so big that you get a bad looking graph that's not accurate. So there we go. 0.1 is pretty good. Okay, everybody, let's take a look at the next thing that we should talk about. How would you move the circle? How would you change the center of the circle? How would you move it right and left? Go ahead and go back to y equals and see if you could do something to make this circle move right, left, up, or down. Change this. Where is the center? Okay, so I'm going to try this. I'm going to subtract 2 from the x's, and I'm going to go up 1. Add 1 to the y's. Now, I'm not really sure, though. Is this going to be a left 2? Is this going to be a right 2? And just to let you know, don't put anything inside the parentheses yet. Again, that's for a later investigation, but it actually is it's not going to move it right or left if you put it inside the parentheses, because this is the actual x coordinate. It's going to be some kind of rotation, which again comes later. Okay, so you tell me, let's see, if it's -2, right or left. Let's take a look at the graph and see what happened. Okay, so to see how it was -2, what you see is what you get. So we're so well trained to say -2 is right, but actually you're subtracting 2 from all of the x coordinates. So -2 will be left, and that +1 will be up. Okay, now let's try and change the radius. So this is our unit circle right now. It has a radius of 1. How do you think you would do that? I'm going to go ahead and delete this. Pause the video and see how could you change the radius. Okay, so did you go ahead and multiply all the x's by 2 and multiply all the y's by 2? And now when we take a look at the graph, notice the radius is 2. So great job, everyone. Go ahead and pause the video right now, and would you go ahead and try number 3 and see if you could fill in the table. Okay, so hopefully you got these values when we were using parametric equations over here. So the question is y a function of x? Now, looking at the table, I'm not sure about that. So go ahead and look at the table and see if any of these values, can help you discover if that's a function of x. Or you might even want to go ahead and pause the video and try and sketch a graph with the points that are given. Go ahead and pause the video now. Okay, so notice that you have a point at 4, -2 and 4, 2. So you do not have a unique y value for every x. So y is not a function of x. It does not pass the vertical line test. It's not a function. But what we're going to do is we're going to try and eliminate the parameter. So if y is t, couldn't you say that x is y squared? Okay, so for the last example on parametrics, my friends, I would like you to look at number 4, pause the video, and see if you can write parametric equations to describe this particular function. Realize that this is not there would not be a unique answer, but I would just try and find something that seems simple. Okay, so it almost seems like cheating, but if you notice that if you let x be t, you could say y equals t squared minus 3t plus 2, and you just described that quadratic parametrically. Okay, so the next thing we're going to talk about are inverse relations and inverse functions. So let's take a look at, go ahead and read about inverse relations, pause the video, and take a look at the graph. Okay, so first of all, we read f to the -1. This is read f inverse, and does not mean the reciprocal. The reciprocal is actually 1 over f. So here we go, everyone. We're going to talk about a function, or a relation, I should say, and its inverse. So an inverse relation is the set of ordered pairs obtained by reversing all of the ordered pairs in a relation. So a comma b is in a relation if and only if that b comma a is in the inverse. So notice we have a point 2 comma 4, we have a point 4 comma 2, we have a point -2 comma 4. Notice we're switching all the x's and the y's. We have 0 comma 0. So the inverse graph of y equals x squared, what we were just talking about, fails the vertical line test because two different y values have been paired with the same x. Again, we did that example last. So notice the original relation paired two different x values with the same y value. So over here, you had -2 and 2 were the x values with the same y value. So over here in the inverse, we have the same x value with two different y values. So next we need to talk about what it means for a function to be 1-to-1. Okay, so a function is 1-to-1 if its graph passes the horizontal and the vertical line test. So let's talk about that. Over here, we had y equals x squared. So notice its domain was all real numbers. The range was 0 to infinity. For x equals y squared, the domain was 0 to infinity, and the range was all real numbers. So notice that the domain of the original is the range of the inverse, and the range of the original is the domain of the inverse, again, because we switched the x's and the y's. So let's talk a little bit more about what it means to be 1-to-1. So notice in my original function, my y equals x squared, my function passes the vertical line test. Any vertical line will only intersect that graph one time. However, if you would do a horizontal line test, notice that your graph does not pass the horizontal line test. So that means when you find the inverse, the graph will not pass the vertical line test. So again, a function f is 1-to-1. Go ahead and read the inverse function. Go ahead and stop and read the definition. Okay, so to summarize all this, a function is a 1-to-1, first of all, if the original relation is a function, and if the inverse of the original relation is a function. So for this particular example, y equals x squared was a function, but x equals y squared was not. So this y equals x squared is not 1-to-1. Also, this is very interesting, the inverse reflection principle. Notice we have this line y equals x. So graphically, there is symmetry to the line y equals x. Okay, so we're going to stop there, and we're going to have the rest of our notes on another video. So go ahead and stop there, and we'll take a break before we start part 2.